Hey everybody, John here. Stick around for setup and programming with the PowerFlex 527. The PowerFlex 527 is one of Allen Bradley's more unique offerings. The 527 must be paired with a Compact Logix or ControlLogix controller, and it programs exclusively using the Studio 5000 programming environment. It also makes use of motion commands. In today's video, we'll go over basic setup for PowerFlex 527 using Studio 5000, as well as use of motion commands. In order to add a PowerFlex 527 to a controller's organizational structure, we're going to start by creating a motion group. It's best practice to give all your axes their own motion groups. So I'm going to name this motion group 1. Having created a motion group, we're now going to add an axis, and this will be the SIP axis for 527. I'm just going to name it PowerFlex 527 Axis 1. I'm going to create. Okay, having created our SIP axis for a drive, we're going to go down here to Control Organizer, and we're going to add a PowerFlex 527 module. So we're going to go New Module, and within the search field, we're just going to type 527, the only module available, and we're going to create. All right, and in our General tab for a module, we'll just name it PowerFlex 527, and we will go ahead and give it our Ethernet IP address. I happen to know that mine is 192.168.123. You'll have to give your IP address according to your system. Now with that finished, we're going to go to our module definition, and we're going to give it our power structure definition. Mine happens to be a 25C-V-2P5, though you have the entire list of PowerFlex 527s available for you. I'm going to say OK to that. I'm going to take heed of my warnings. And all right, we have created the module for the 527 and the axis. We're going to say OK to this. I'm going to close this. And then we're going to go back to our module, right-click, and select Properties. Now we've already outfitted the General tab. We're going to go down here to Motion and Associated Axes. We're going to choose the axis we just created, 527 Axis 1. We're going to apply that axis, and then we're going to modify our axis as needed. And I should say that all your 527 modules will have to be associated with an axis. Okay, now we're in the General tab for Axis 1, and we're going to set up our axis for our motion. And to get us started, we have axis configuration. We do have motor feedback. We're using position loop, though you have your choice of velocity loop or frequency control. We're going to use a basic application type, and we're going to use a loop responsive medium for today's demonstration. Do feel free to change these according to your application. Our motion group is already set up for motion group 1, and our update period is 2.0. We're going to change that from 2.0 milliseconds to 4 milliseconds because that is the best practice recommendation from the manual. So right now we're in our base update period for our axis. We're going to move it to alternate 1 with 4 milliseconds. We're going to click Apply. We're going to say OK. Now then, with that set up, we're going to go to our motor, and we're going to pick a rotary induction motor, and we're going to define our motor data. Now I happen to know that my motor is a 25 watt, 230 volt motor. You'll have to enter your motor data in according to your own system. Right, I've entered my motor data, so I'm going to apply that. And now I'm going to go to motor feedback. I happen to be using an encoder. It is a quadrature encoder, and it is 1024, so all this information is correct. And I'm going to click Apply. So with that, we set up our axes, we set up our motor data, and we set up our feedback data. Now we're going to head to scaling. And within scaling, we determine how many rotations are equal to a position unit. So in my case, 1 position unit is equal to 1 rotation, and that is perfectly fine with me. Next, we're going to go to torque and current loop. It's a best practice to set up your peak torque limit positive and negative to plus and minus 200 in order to have optimal performance from your PowerFlex 527. We're also going to go to exceptions, and we're going to make motor thermal overload user limit. We're going to take that from disabled to alarm, and we're also going to go to excessive position error and take that from disabled to ignore. These are best practice recommendations from the manual to ensure that your drive is capable of auto-tuning effectively and operating effectively as well. Now with that, we're then going to go to our parameters list, make sure that we're inside of all, and we're going to set our current velocity limit to 180. And we're going to go down to our feedback 1 velocity filter taps and set that to 16. And that's a best practice recommendation from the user manual. We're going to apply that information. And with that, we have set up our axis. Going to say OK to here as well. And we can go ahead and engage in motor testing. So we're going to go online. And I've already set up the communication structure for my PLC and drive. You're going to have to do that for yourself using RS Links Classic or Factory Talk. We're going to download our freshly made program to our PLC and drive. Give that a moment. All right, and we're going to set ourselves into remote run. Okay, with that completed, we're going to go back to our axis, go inside of properties, and then we're going to go to analyzer, and we're going to do some motor testing. 3 test choices: calculate, static, and dynamic. Dynamic is the most accurate. The dynamic will of course make the shaft of your motor spin around. If that's a problem for your setup, you can do a static test, not quite as accurate, but much better than nothing. We're going to go with a dynamic motor test, and we're just going to go ahead and start. We're going to give a moment for the test to execute. And it may take a few moments for this to happen, as much as 2 minutes as a matter of fact. And of course your motor will move and chatter while this goes on. And the test passed. We're going to say OK, and we're going to say accept test results. With that undertaken, we now have the option to go to the hookup test. This is simply a way for you to verify that what you have programmed in your drive as the forward direction is in fact the forward direction as far as your process is concerned. If it is not, you can then take this test data and either rewire your drive or change your polarities. But we don't need to do that because our demo kit has already been set up in the way that we want it to. So we're just going to go ahead and go to an auto tune. And we have a rigid hookup, though you have a choice of a compliant hookup if that is your situation. We already picked a loop responsive medium and application type of basic, so we're going to keep those as is. And we're going to come down to your travel limit. Maximum travel limit in this case is something like 2100 position units. I'm going to use 2000. You want to set that as high as you'd like or high as possible. And position units, I have a 1600 RPM drive, so that's about 26.6 units per second, considering the fact that I've set 1 revolution to equal 1 unit. Obviously, if less than 1 revolution is equal to 1 unit or more than 1 revolution is equal to 1 unit for your application, you'll have to change this accordingly. But for now, we're going to use 26. I'm going to use 100% rated torque and forward unidirectional. Again, this is for our application, but you have a choice of reverse unidirectional or bidirectional. Now with this set up, we're going to go ahead and start our auto tune. And that happened very quickly. Of course, I don't have a very big motor. The larger the motor gets, the more time an auto tune may take. Now, with that done, we're going to accept our values. Now, we have set up our motor, set up our axis, and tested our axis. We are good to go with motion. And we're going to test some of our motion by saying OK. Going back to axis, saying motion direct commands. I'm going to start our axis, motion servo on, by executing. And of course, I'm pointing to the axis we just made. I'm then going to go down to jog. I'm going to make a jog at 10 units per second, execute. And our unit is jogging. Now I'm going to stop the unit. And I'm going to turn the axis off. And there you have it. And that is how you set up a PowerFlex 527 for use with a Compact Logix Motion PLC. Having created an axis for PowerFlex 527 and added our 527 to our logic structure, we're now going to go ahead and create a ladder logic program to add motion instructions. To get started, we're going to go to Main Program, and we're going to add a new routine. We're going to name that routine PowerFlex 527. Okay, with our new routine added, I'm going to dive right in, and on our first rung, we're going to add an exam if closed and a motion axis on, or MSO command. Motion axes have to be turned on before they can undertake instructions such as motion axis move or motion axis jog. So this first rung is going to let us do that, and our normal open is going to be associated with a digital input on our PLC, digital input 2, which itself is being controlled by a 2-position switch in my demo kit. And for our motion instruction, motion axis on, we're going to associate that with our PowerFlex 527 axis, and we're going to give it a motion control tag. I'm just going to right click and add a new tag. Motion instructions have to have a motion instruction tag because the instruction itself does not contain a data table. The tag is where the data will reside. And I'm just going to name this tag MSO1. One best practice for motion instructions is to give them unique tags. That way each axis can have its own motion axis on instruction, helping you program things more efficiently. Now that my rung has gone gray, meaning that I have added my motion axis on command, I'm now going to add another rung, and I'm going to add another exam if closed and a motion axis off, or an MSF. I'm going to change this command actually to an exam if open. And this is going to be the other side of my 2-position switch associated with data 2. Now then, I'm going to associate my motion axis off with my same axis. And I've already made tags for this just to make things a bit simpler, but I have MSF1, and notice that this is a motion instruction tag. You could conceivably go into your controller tags and make all of your motion tags first before making your logic, or you could make them in place, whichever suits you best. Now I can turn my motion axis on or off. So now I'm going to add another rung, and I'm going to add a branch. Now, one side of this branch, I'm going to add exam with open. On the other side, I'm going to add another exam with open. And I'll explain this part later, but in this end, I'm going to add a ladder element, a motion axis move. A lot of different elements to a motion axis move, and we'll go over each one of them. Now, firstly, we'll add our axis, and then we have to add a motion control tag. I've already made one, and I've simply called it motion axis move 1. And then we have our move type. There's 6 different move types for motion axis move. Type 0 is an absolute move, which is in reference to home, and type 1 is an incremental move, which is what we're going to be using today. Next up, we have our position. Now, I could type a value directly into position. This is a dual integer style value, or I could make use of a tag, and I happen to have already made one, position 1, and I've put a value into it, 50. Now, position, speed, acceleration are all dual integers, and they can each be associated with a tag so that you can write into them as your process is undertaken. It's often a good idea to use tag values for these, simply to make adjustments of your motion axes a little bit simpler. Now then, we come up to speed, and I've made a speed tag also, speed 1, and I've given it a value of 10, and I'm going to input my speed units. You have your choice, but we're going to use units per second. And remember, in my case, 1 unit is equal to 1 revolution. Next, we have our acceleration rate. I also have made a tag for that, ACC1. I have a value of 10, and that's going to be units per second squared. We have a decel rate. I'll just use that same acceleration tag, and I'm also going to give this units of units per second squared. Next, we have our profile, and you have your choice of trapezoidal or S-curve. This is just like a PowerFlex 525. Trapezoidal means you will accelerate and decelerate linearly, whereas S-curve attenuates your acceleration and deceleration time, allowing you to ease into material and perhaps have smoother startups and stops. But for our demonstration, we're going to use trapezoidal. Next, we come up to accel jerk and decel jerk. Accel jerk and decel jerk is the rate of change of acceleration and deceleration, and it has to do with how things perhaps jostle when a conveyor or the moving system starts or stops. Best practice is to give your accel jerk and decel jerk values of 100, and your jerk units should be set to percent of time. This is a good starting point for most motion axis application. If you notice too much jerk at the start and stop of your process, you can come back into this command and adjust these as necessary. Next, we have merge speed and lock position. The merge command, if enabled, will simply allow a command to cancel a current motion axis instruction so that a different instruction can be undertaken. So we're not going to make use of these, but you will have to resolve all of these question marks if your instruction is going to function properly. So my merge speed I'll just set to 0. My lock position I'll set to 0. My lock direction I'll say none. My event distance 0, and my calculated data I will also set to 0. Now I've got my motion axis move instructions set up. These normal opens I'll come back to in a second, but for now I'm going to add another rung, and I'm just going to add motion axis stop, or MAS command. Motion axis move allows us to move. Motion axis stop allows us to stop motion. And I'm going to associate this normal open with a red push button on my demo kit associated with digital input 0. And for my motion axis stop, I'm going to choose our axis. And I have a motion control tag already made for it as well, MAS1, excuse me. And I get to choose my stop type. I can stop all motion, only jog motion, move motion, gear motion, etc. But I'm going to stop all motion in our case. And I'm also not going to change our deceleration rate. But again, I have to resolve all question marks before I can move forward. So I'm just going to give it the same deceleration rate as our motion axis move. Decel jerk, I'll just set to 100. Actually, decel jerk, I will not change, excuse me. Decel jerk, I'll set to 100. Jerk units, I'll just make percent of time. And there we go, we've added a stop. Now to discuss these normal opens, I'm going to add another rung. I'm going to add an examine, if closed, and a time on delay. Now the reason why I'm adding this, I want my motion axis move to execute, and when it finishes, I want it to dwell for 2 seconds and then execute again. And I'm going to do that by using a time on delay. Now obviously time on delay is not a motion instruction, but it's convenient to my demonstration today. And I'm going to make this normal open associated with my motion axis move, and I'm going to use motion axis move PC output. Motion instructions have multiple outputs. You have the EN, DN, ER, IP, and PC. The EN output becomes true when the rung that the motion instruction is on goes true. The DN output bit goes true if the motion instruction has been initiated properly. The ER bit goes true if an error occurs. The IP bit goes true if a motion instruction is being currently undertaken, and the PC bit goes true if a motion instruction has been effectively completed. So DN goes true if it starts properly, IP goes true if it's being undertaken properly, and PC goes true if it finishes properly. Now then, for my time on delay, I'm going to add, actually I've already made one, come to think of it. I'm going to add a timer tag, which I've already made, and I have a value of 2000, which correlates to 2 seconds of delay. So when my motion instruction properly finishes, this rung will go true. I will then delay it by 2 seconds, and to input that on the first part of my latch, I'm just going to give it a data input of 1, and that corresponds to a green push button. So I have a push button to start my motion. And then to latch my motion, I'm just going to use my timer tag DN. All right. So when the timer starts and then 2 seconds completes, it will then cause this motion instruction to start again. Okay, I'm going to reduce both of those. All right, now I've added all my instructions. I'm going to go ahead and finalize my edits. And those edits have been finalized. I'm now going to go to the main routine. And I'm going to add a jump to subroutine. I'm going to associate that with our new subroutine, PF27. And I'm also going to finalize those edits. And my rungs have gone green, meaning I'm ready to go. So with that, I'm going to turn our axis on. And our axis has turned on. And now I'm going to start motion by pressing the green push button. I'm in progress. My motion completed, my timer is timing, and I'm back in progress. And that is how you program a PowerFlex 527 using motion instructions. Thanks for watching, everybody. Check out the show notes for some useful links. Do please remember to like and subscribe, and have a good one.